University Video Communications, with the sponsorship of IBM Corporation, welcomes you to this edition of the Distinguished Lecture Series, Leaders in Computer Science and Electrical Engineering. Today's speaker, Fran Allen, the first woman IBM Fellow and a member of the National Academy of Engineering, is Senior Manager of Parallel Software at IBM's Thomas J. Watson Research Center. She received her BA in Math from the State University of New York, Albany, and her MA in Math from the University of Michigan, Ann Arbor. She's recognized for her work on the theory and practice of program optimization. This lecture focuses on a subset of the challenge of optimizing compilers for parallel computers, parallelizing FORTRAN for shared memory, parallel computers.
The topic of this lecture is optimizing compilers for parallel computers. Let me start by saying a few words about optimizing compilers for unique processors. This is a work that has been going on for many, many years, and which is the basic goal of that work has always been to deliver the performance of the unique processors, the underlying hardware architecture. But a secondary goal has been to make it easy to use and to provide portability from one system to another system. Now, as we've started to move into the era of parallel computers, we have some new challenges in this area. We have to, again, deliver the performance of those parallel computers, and they're very different problems than we had before, but we again want to be able to provide portability between the different kinds of parallel computers that are coming into existence, and there are many, many different kinds. And we also want to make the use of parallelism easy. Now, the scope of what I'm going to talk about then is shared memory architectures. And this means architectures where there are multiple processors. Each one can address all of memory, let's say, all of it addressing out of a same virtual shared memory space. And there can be a few processors, maybe 2, 4, 6. There could be many processors. I'm not going to be concerned about that because for one thing, we want to look at the question of portability. And the other thing is being able to automatically form processes. Now, that's going to provide ease of use as we move across from one architecture to another. And so the user doesn't have to be involved as much into actually forming processes in the program. I'm going to limit the talk also to FORTRAN-like languages because this is an area in the engineering scientific arena where there are many programs and where the performance for those applications which those programs support is extremely important, and one of the reasons why parallelism has become of great interest to the engineering scientific areas. The lecture topics here that I will be discussing is actually finding the parallelism in these programs, and then having found the parallelism, and that's very much dependent on how the programs are written and our ability to analyze and understand the programs. And then once having found the parallelism, forming useful parallelism for the particular target architecture. I'm going to separate those. And then I will be trying to put this all together, giving a perspective of how one, first of all, would design a compiler to do this, and then secondly, where the compiler kind of fits into the larger system in which it naturally resides. In fact, one of the things I'd like to stop and say right now before I get into the specifics of the finding parallelism as the first topic is the fact that as we are starting to develop systems for parallelism, we're needing to be able to consider the compiler, the operating system, and the user, and all the other components of the system. And the user is really a component of getting the performance from the machine. We need to form some way of integrating and working together. And so we can no longer think of these components as being separable black boxes, or a user is not a black box, but separable units, each in which we just try to put together through some very formal interfaces. We've got to look at it as a whole. So I'm wanting to spend some time at the end on how we can put all of this together, and so it can become a cooperative processing. And lastly, some open problems. Before I go into it, I want to give certainly major credit for the ideas, first of all, to Dave Cook and his colleagues and students at the University of Illinois, which really founded much of the area that I'm going to be talking about. And I'll mention the PTRAN group at IBM Research These are my colleagues on which we've been developing some of the work I'll be describing. Now, the first topic is on finding parallelism. I'm going to give some examples on region or non-loop parallelism, on loop parallelism, which is the most traditional area that we look at. Then I'm going to describe data dependence analysis. This is the way of deducing parallelism in programs, and on control dependence analysis, which is related to that. Then the forming of the maximal parallelism that the compiler could find in a program. And I'll bring up interprocedural parallelism, which is relatively new, but extremely important in the formation of parallelism. The first three charts are on examples. The first one is process formation across regions, or this is a so-called non-loop parallelism. If we look at this example, I have a region 1 where we create arrays A and B, region 2 where we use A and B to store into the even elements of C. And in region 3, we're doing the same thing, only this time we're storing into the odd elements of C. 2 times I plus 1 is a reference to an odd element of the array C. And then we would use array C. And now region 2 and region 3 can be executed in parallel. Now, perhaps the do loops themselves could be executed in parallel, but the point of this chart is the recognition of regions in the program, region 2 and region 3 here, which can be executed in parallel. Now, this would be particularly important, say, if the inside of each of those do loops, say, contained calls to procedures or had, of course, elaborate amounts of code in it. And, but I'm going to discuss the actually formation of useful parallelism later. In the next chart, process formation across do loops. This is the traditional thing that optimizing compilers for parallel computers have concentrated on. Nearly all of them concentrate on this particular case. The idea here is to look at a do loop and see whether that all of the iterations can be done independently. Now, in the example, the inner loop, do I equals 1 to 100, all of those iterations are independent. And that's shown on the right-hand side, indicated as a do all, which that means that all of those could be, all 100 iterations could be executed independently in any order. Now, why is that? Even though one is referencing A of j minus 1I on the right-hand side of the equal sign, on the left-hand side, A of j I, there's no relationship here between, no dependence on the different iterations of I. There is a dependence, however, on the different iterations of j, because on the right-hand side, I'm referencing something that's been stored into a sub j minus 1 on a previous iteration, a sub j. So I can't execute the iterations of the j loop independently. And this is one of the most important constructs to look for. And as we'll see a little later in one of the charts, what we will want to do is reform this code so that we have more parallelism within the loop. Now, what will really happen here is that we can, looking at the right-hand side, the do all I equals 1 to 100, it may not be worthwhile to form 100 different independent parallel processes, each of which we will need to have some sort of way of starting up the process, some way of coordinating it, say when we get to the end of it. And because each one of those hundreds is being done 100 times, we may want to revise this so that we cut down on the cost and increase the amount of work we're doing. And that's what we'll talk about when we get to the formation of useful parallelism for the given target architecture. But long before we do that, I want to look at how do we find parallelism in the code. We've looked at a couple of examples, and what we want to do is to say, how are we really going to detect this within a compiler? Well, one of the major keys is dependence analysis. This is really the fundamental piece of work that has to be done in order to determine the reference patterns at the element level to storage. We're looking at FORTRAN programs, the way they've been written, where they are referencing elements of storage. I'm not talking about, they're not array, even though we talk about them as arrays. The code in FORTRAN programs looks at storing and using elements out of storage. And it's extremely important in order to be able to detect parallelism and independence is to understand how those references to storage are being made. So dependence analysis is an analysis to look at that. And one of the things we need to be able to do is find out when there is a relationship at that element level to distinguish the true data flow and where the true flow values through the program, and distinguish that from storage reuse. In a language like FORTRAN, we're reusing storage all of the time. And what we really also want to know is the temporal distance between different reference relationships, so that when I'm storing something into storage, I might maybe be using it maybe 20 iterations later in the do loop. That's an important piece of information, whether it's 20 iterations later or 1 iteration later. So the temporal distance is another factor. And then, having found all of the dependence analysis, then we want to form processes to satisfy these dependencies. So let's take a quick look at what the dependence relationships are. And this is just a few examples of dependence relationships. This first one is an example of the very important flow dependence. Within the loop, I am storing into an element of A sub I, and then in the same iteration of the loop, I'm going to be loading from that element of A. And some value is being transmitted from the first reference to storage into A to the second use of A. And I probably get an incorrect answer if I violated that. So I must keep that flow dependence. Here's another example of flow dependence. Information, the value is being transmitted by the program. However, it's carried by the loop, because where I have A sub I on the left-hand side, in the first statement in that loop, I'm storing into an element which will be used on the next iteration of the loop, where I have A of I minus 1. So I have to retain that, and in fact, this particular loop could not be executed as a do-all, where there's no coordination between iterations of the do, and where they could be executed in any order. Now, here's another example of dependence. It's so-called output dependence. This is where storage is being reused. X in this do loop might be an example of, might be a temporary value that is used somewhere else in the same do loop, and the next time around the loop, I'm just using that temporary cell again. There is no information between different iterations of the loop being carried in that location. So if I can break this reuse of storage between iterations, and that's something we're going to try and do, then we can, and in fact, execute this loop in parallel. So that's going to be one of the things we try to do. Those things that are storage dependent, we will try to break that. Now, the basic idea with dependence testing then, in order to determine what the relationships are, is to formulate a linear equation of these relationships between two subscript values of interest, and then see whether there's a solution to that equation within the range of the values of the loop, iteration variables. Let's go through a rather elaborate example here, and the reason I've made this elaborate is so that you can't guess whether there's a dependence or not. If you look at the top of the chart, I have do I equals 1 to 10, and then I have a subscript of A, which is 3 times I plus 5, and so a value is being stored into whatever that location is, and in the loop then I'm further down using something out of another element, or maybe it's the same element of A. The question is there any relationship here? Can I form that into that do loop into parallel processes? And the way we look at this then is that we say, is there any value for I between 1 and 10, okay, which satisfies the equation? We actually form this as an equation, taking the first subscript, 3 times I plus 5, and we say, okay, let's say that's x. X is going to range from 1 to 10. And the second subscript, well, let's call that introduce the variable y, then y is going to range from 1 to 10 also. Is there any solution to that equation in that range? And in fact, we find out that when x is equal to 4 and y is equal to 2, we do have a solution within the range, which means that, looking back up at where those equations came from, the assignment is made when I is equal to 4, and the use actually is going to happen when I is equal to 2. That means there's an anti-dependence here. There's a reuse of storage. As we iterate through the loop as it was originally written, we'll be assigning into the same cell in I, which had been used in an earlier I equals 2 iteration. So one of the keys that we need to have in this is to be able to do this rapidly and to express this succinctly. This is the key, doing this very well. And to the extent that we're able to look at the references to storage is really going to determine the extent to which we can find parallelism in programs. So we do this analysis, we actually then represent it by saying if we have the nodes representing statements and arcs representing dependence between these, we can build a set of dependence graphs which give, with the arc labels, the dependence type, whether it's a true dependence, an output dependence, a flow dependence, whatever kinds of dependencies. I haven't gone through all of them. There's a large number of these. And in fact, we can augment this information by saying what is the distance from one iteration to another, if we're looking at in the do loop case, to when these dependencies exist. This is an important and very critical part of forming parallelism in programs. Now, another thing that's important is understanding what is the relationship in terms of the conditionality of execution. In the case I have here, we can do a lot of dependence analysis. This is pretty easy because we don't have any subscripts in this particular case. But there's still a question, when are the statements here executed? By looking at this program, and this is very simple, we might be able to, going back down into the if test, in the if conditional part of this, that the two statements where y appears on the right-hand side could be executed in parallel, quite possibly. Okay? And there's a lot of other things that might be able to be executed in parallel. Now, a program, of course, can be very large. There can be hundreds and hundreds of statements. There can be many different ways of forming the conditional relationships in the program, as well as the dependence relationships. Not only do we have to get the relationships expressed as carefully as we can, we need to be able to do it as quickly as we can in order for these compilers to be able to be reasonably fast. I mean, if we spend all day forming parallelism, we probably have lost some of the value of this. We need to be able to do it rapidly. So a part of the thrust of our work is to be able to look at this, find ways of recognizing these relationships. And one of the ways for this particular one, for example, is something we call control dependence. And where we build a control dependence graph which expresses the essential ordering of the program, not the way it has been written, because of course it's been written usually in a linear ordering, and which then expresses the relative execution conditions of the code and really initially ignores the data dependence constraints. We want to forget about those for the moment. And here's the example that we just looked at where we have drawn the control dependence graph, and we could in fact look at this and say, well, the first statement beyond the do, which is an assignment to x, could be executed at the same time as the if test. Maybe it could be. We didn't have enough detail on in our little example, which could have been executed perhaps at the same time as the z, which was way down at the end of the do. Maybe you didn't notice that. So they have the same conditionality for execution. Now if we go down to looking under the if test, where we took a true branch, there were three statements, y equals x, and a couple of uses of y, and those all have the same conditionality of execution. So at this level we can say, okay, they can all be executed in parallel, but of course they can't. We need to be able to constrain this kind of graph with the data dependencies that we just talked about. So we've identified something called a program dependence graph, which is the control dependence graph where we add to it the data dependencies that we've extracted from the program. And this is really then forms a basis for our forming of maximal parallelism. Let me just show you the program dependence graph for our same example where I'm showing the true dependencies here, not all of the dependencies. And this then says that as far as this graph is concerned, I have a true dependence that shows the true dependence from the definition of x to the use of x, and from the definition of y to the two uses of y. And those are true dependencies and what we are going to have to honor to get the correct program. I haven't shown on this graph the fact that they're on different iterations of the do. I have an output dependence between the reuse of storage for x and also the reuse of storage for z and the reuse of storage for y. Output dependencies and reuse of storage we may be able to do something about. So this particular graph then, and this is where we do our work, shows the maximal parallelism that this little fragment of code has. And it's from this and from transformations to actually get rid of the other dependencies there that we will then ask the questions, what's useful for whatever our target architecture happens to be? Before we go into that, I want to talk about interprocedural analysis. which is very important because many programs, of course, are written with multiple procedures, and many target systems want to have large units of code that are running in parallel. So we would like to form processes containing calls and form processes and call procedures. And so we need to be able to understand the flow of information, flow of values throughout the entire program. Here, I might want to ask two questions. First of all, let's look at the call, which is inside that loop 1 to n. I'd like to be able to ask the question, can that do loop be executed in parallel? That really is saying, can I have multiple executions of the called procedure R going on at the same time? And in order to be able to do that, I have to look at R and understand a lot about R and everything else, everything that it calls, understand how it uses the arguments that are passed to it, how it uses the global variables, anything that's visible across these boundaries. So that's one aspect of interprocedural analysis. A second aspect of interprocedural analysis is just looking at this particular routine itself. How do I know how x and n, which are parameters that are being passed into this procedure, how are they related to each other? What are the aliasing relationships here? Is n, in fact, do we know whether there's a constant value for that, which would be very useful in understanding how to break this program up into parallelism. So an important aspect of what we do in the formation of parallelism is, in fact, to look across procedures. And I'll come back at the end of this in order to say how we can tie a lot of this together. So interprocedural analysis techniques, aliasing analysis across procedures, and within procedures too, of course, we need to understand all of that because we need to understand reference patterns. We need to understand all the side effects in a language like FORTRAN, which is called by reference language. It can be great in lots of shared variables. It can be great many side effects. Some languages are much better, of course. And we want to be able to do constant propagation, refine our information, and understand the storage map. Really underlying all of this is a storage map. And I'll come back to the program database later because I think that that's a key to trying to integrate a lot of this. So where are we in our talk? We have completed the analysis of the program. We may be able to have the maximal parallelism in the code. And now want to say, can we form useful parallelism for the particular target architecture? I should comment at this stage that the techniques that I've described, which are the techniques that go in and deeply analyze a program, are, I think, very limited yet. There are many, many ways of expressing a program where one will not be able to find parallelism and where the parallelism is truly there. One of the things that we have trouble with, for example, is where there's any levels of indirection. Sparse matrices are typically stored with levels of indirection. Very hard, almost impossible to deduce whether there's independent references to storage in such a system. So complementing the kind of the technologies that I'm talking about here, which are technologies inside the compiler, has got to be information from the user and certainly parallel language so the user can explicitly express some of the what's going on in his program. Okay, let's turn now to the formation of useful parallelism. We want to be able to form useful parallelism for programs where we've found parallelism by the compiler and where the user has explicitly expressed it. And we want to be able to form it in both of those cases so it maps it on to the specific target architecture. So what are the technologies that we have? We want to form useful parallelism by transforming the code that we have to get larger or smaller or whatever units of parallelism. And we want to do data transformations to get rid of these references to storage that are just reusing storage. And we then want to, based upon the target architecture, then form the useful parallelism. Okay, what are the kinds of code transformations we want to do? We need to form independent units of code, dependent code if we can, increase the size of potential processes. Here are some examples of code transformations. Loop interchange, loop distribution, there's dozens of these, by the way. And then sequencing, maximally parallel code. Because these little fragments were not very useful. Let's go back to the example I had earlier, these two do loops, where we were able to form the inner do loop into a do all. Now, and the outer do loop was going to be executed sequentially because of the way the reference patterns to storage due to the J subscript. Well, now that's not a very efficient program, but so we can do loop interchange as an example and get the parallel processes on the outside and have the inside each parallel process have this 100 iterations of the J loop, much more efficient than the original transformation. This is a simple example, but one that's, of course, important. Another aspect of this, as I said, was the data transformations. As I've said before, storage reuse inhibits potential parallelism, and so we want to get rid of that, and an ideal solution here is to go to single assignment. Okay? This is one of the points that the people who have been working with functional language, single assignment languages have been saying. The data flow languages all have this point also. And in fact, there's some technologies are emerging now to transform FORTRAN programs internally into something called static single assignment, and where we try to move in that direction to break the storage reuse. Here's an example of a static single assignment or single assignment. This is actually happening at execution time. It's where we have at the outer loop, we do again I have the reuse of X. I can make X private for every iteration. If I form the outer loop into multiple processes, I can make, for each process, I could have a private copy of X. Now, that then is going to be at execution time a single assignment of X for that iteration. And I have to, if I have nested processes such as this one, where I have a J, if I form the J loop into multiple processes, then even though X is private in the outside process, it's going to be shared internally, and Y itself will be processed. So this can be, there's a lot of work can be done with changing the attributes of a variable in terms of its use within a process. There are many other kinds of transformations to reduce the reuse of storage and the inhibiting parallelism. Okay, now that we've done as much as we can with the program, found the parallelism and transformed the program to express more parallelism, then how are we going to package this up for the particular underlying architecture? We want to minimize, of course, the execution time, and to do this we want to balance off the process size, the available resources, the number of processes I think I'm going to have at execution time, and the communication cost. There's always a cost with starting a process. There's a lot of work being done. In reducing that cost, there's always some cost associated with that. And we need to balance that off. Let's go back to the graph we had earlier, which showed the maximal parallelism is constrained by the dependencies in here. What we want to do is to form the useful parallelism out of this. It's most likely that having X and if and Z as separate processes, which they could be, is not going to have a big payoff on a lot of systems, because the cost of starting up, if they're just single statements, is going to be far too great. The technologies that we use is to take this potential process graph, the maximal process graph, and starting with that, then using a parameterized economic model, which accounts for a lot of things about the program and about the target architecture, then bundle this maximal parallelism back up into useful parallelism. And the input to this economic model would be things like the loop frequencies and branch probabilities. That can be guessed at, or in fact we can get that by previous executions of the program where we've collected up actually information at runtime and held that. And then we do an estimate, can do an estimate about how much, what the execution times are going to be. In fact, in the system that I've been working on, the PTRAN system, we actually go down and estimate the cost of doing a load, the cost of doing an add, the cost of doing a multiply on the given target architecture. And we make a guess also at the number of processors that are going to be there, though in fact we could postpone some of that until execution time. The question of binding in all of these systems, when do we bind information, is very interesting, because what we're doing is really trying to make decisions when we can make the best use of the information. So we try to make decisions at compile time, make decisions at execution time, and sometimes get the user involved and spread the decision making out, and even about individual aspects of the system, like the number of processors. We don't know at compile time necessarily, if we're not going to have a dedicated machine, how many processors are going to be available. So, or how many we can use if we have a do loop that goes from 1 to n. So some of these decisions we have to be quite flexible about. And we need to, of course, know the overheads for process initiation and termination. Okay, how can we build a compiler out of all of this? Okay, that puts all of this together. And I must say there's a lot more to this, of course. I've just kind of skimmed across the top of the different areas that need to be considered. Well, and as I mentioned earlier, we need to make such a compiler relatively fast. The extent, the extent to which we can make each part of this rapid is going to very much determine how the extent and the depth of the analysis that we can do, that the user will tolerate. Let's put it that way. And so it's important to try and make every part of it rapid. So how do we make such a compiler? We can, of course, translate into some internal form. The preferred internal form is very close to the source form, where one can actually has the subscripts, can see the do loops, and has the information in quite a compact form, because one needs to be able to look at a lot of information. And so one doesn't want to have expanded it out to some very low-level text form, which may be more suitable for a more machine-dependent optimizer, where you're interested in moving loads out of loops and so forth. You really expose much too much information at that level. One wants to be able to look at a much higher level internal form. Having translated it into that internal form, then one can build an interprocedural call graph. And you can actually do that on the basis of information that has been collected during parsing. During parsing the program, in building the internal form, one can collect up little pieces of information about calls and the subroutines, and in FORTRAN's case, the common blocks, and so forth. That can be just put in the side. And then having collected that information about the call graph, then one can look at that particular isolated piece of information and not have to look at the whole program again, or even the subparts of it, and do alias analysis and understand how information is being passed forward through the call graph. Now, if you have recursion, if you have loops in the call graph, then there will be some limitations as to the value and how precise one can be. This can be a very, very fast process, since in particular it doesn't involve reanalyzing the program. The next thing then is going bottom up in the call graph. Now, the idea of going bottom up then is starting with the leaf procedures in the program and doing a deep analysis in order to be able to understand all of these data dependence relationships to form the maximal parallelism in the particular subprogram, and deciding whether there's useful processes in there, forming the useful processes, and then saving the results of these for calls to those routines. And so when it's collecting, doing very, very precise analysis of the subprocedures, collecting that information and then passing that back up, so that when one sees a call to a procedure, one has a great deal of information about it, and what variables are being changed, what variables are being used, and in fact, what processes have been formed in that procedure. So what decisions have already been made about what the cost of processing will be, and then of course generate code. Let me give you a summary of what is happening overall. Within each one then, we're deducing the temporal reference patterns and the aliases and storage layouts, and deducing that information, and then identifying the processes across the loops, across the regions, and because we're doing interprocedural analysis across procedures. Now, we then are restructuring the code and the storage to expose more parallelism, and then forming these into processes to match the target system. Let me sort of repeat here a little bit about the role of interprocedural analysis. We really are looking in depth at each procedure, but with knowledge about the procedures that it's called. We're not taking, and just because I think it's far too expensive, analyzing at each call site the total effect of all the procedures, analyzing the entire collection of procedures that are called. Now, of course, as one goes down through the system, one needs to understand not only the sort of things that are interesting for forming parallelism, but one needs to understand what's happening in terms of I/O, because one doesn't want to form parallel process of a call to where the called procedure or something that it calls is doing input or doing output. One could really, so that and many other things need to be factored in. And in fact, much of what I've described here is of interest and value in
optimizing programs for uniprocessors. One would do some of the things a little differently, wouldn't necessarily, one might reorder the code, but one wouldn't necessarily, of course, be interested in forming useful processes. But most of what I've been talking about is a value for extended optimization techniques for uniprocessors, and I think that this is an area we really haven't explored very much yet. We've developed a lot of new technologies for this parallelism. We haven't really thought very much about bringing this back into making better uniprocessor code, particularly for machines that have deep pipelines, the superscalar, super pipelined uniprocessor machines. We want to have a lot more instructions in the inner loop, a lot more independent instructions, and in fact, in some ways, those are really micro-independent processes that are in there. So a lot of the technologies I'm talking about have applications to that. Okay, let me go to the larger question here of where does all of this fit in? I've talked about the compiler just in some very sketchy way, but we're talking also about a total system where the compiler is just part of this total system. And one of the things I see as a centerpiece of this is some emerging ideas, which I've called a program database. I think most people do call it that. I think it's a bit more than that, is some way, though, of collecting up information from the user, from the compiler, from the execution of the program for use by the user, the compiler, and at execution time. So let me give an example of this. The compiler, while doing the analysis, understands a great deal about the program, probably, in fact, a lot more about the program than the user and the individual user really understands about his code, because he's probably using subroutines that he hasn't seen or he didn't write, and we can provide that information to the user. The compiler knows, for example, what the references to storage are in some fairly deep ways. Now, some of those are incorrect, are not nearly as precise as it could be, but however, we could give that information to the user, and the user could, in fact, augment that information. Another thing, during execution time, we can collect up information about the performance of the system. Keep that information in the program database, and then so the user can look at it and the compiler can look at it for future compilations of the same job. One of the key challenges I think we have right now is having such a system, bringing some of this together. I think that we need to be able to, in fact, architect a system, architect I call it a program database, but architect an interface here where all these components, the tools, and the compiler is really a tool here, can start to communicate around this central repository of information, can add to it and take information out of it in order to get the performance. And where the user can add information to this, or one can bring in an expert system where details about the parallel hardware underneath can be added in and used by the parallel system. So this I see as one of the very interesting challenges that we have, and so something where we can all start to cooperate on building tools rather than have separate independent tools and which are not cooperating properly, I think. Okay, here are some of the other open issues, and there are very many of these. Automatic data partitioning. Let me mention that I focused here on tightly coupled shared memory architectures. We have very little technology when we go to more loosely coupled systems, clusters of computers, or even distributed systems. I think that distributed is going to become part of this whole question, and maybe it already is, but we need to start to look at it. And one of the issues is going to be, how do we partition the data up so that we can ship big chunks of data to other processors which may be some distance away, And we need to be able to have techniques to be able to do that. We don't have them today. I'm not sure that we will be able to get them, but it's a very interesting open problem. Right now, the user has to do all of that, and it's going to be very specific for the particular machine, message passing machine or distributed system, whatever. We need to understand more about incremental compilation and the whole question of this integrated system. We need to understand how to get our analysis much more precise than we do it today. We need to look at storage hierarchy management. All of these machines have hierarchies of storage. Even if it appears as if there's just a single memory, there's caches and everything else that these need to be managed. We need to consider lots of other computational models. The tightly coupled share memory is just one, and probably is one that we need to put aside for the moment in terms of focusing where we're going to do our work in compiler technology and language technology, and to look at the other computational models, which I think to some extent we have been ignoring a little bit too much and saying, okay, the user will do it. And we need to look at involving the user in our work. Okay, I want to thank you very much, and I also hope to see a lot of results coming on this area. It's a very exciting area and a very important one. And I've indicated only a few of the important open issues. There are many, many more.